so we talked about one shape of curved mirror, and now we need to talk about the other shape of curved mirror. Some of the resources that you'll find like to describe these shapes in terms of being concave and convex, which is fine. The other mirror that we were looking at is a concave mirror, and this is a convex mirror. But the thing that I think is more useful when it comes to talking about mirrors is to talk about them as converging and diverging. The mirror we talked about earlier was a converging mirror, and we're going to see what I mean why this is a diverging mirror. So, just like we did last time, the first thing we want to do is see what happens when we have a group of light rays that come in parallel to the principal axis and figure out what happens on our mirror. Now, the shape of this mirror is different from the mirror that we had before, obviously. But every time a light ray reflects off of a mirror, it's going to follow the law of reflection. The reflected angle is always equal to the incident angle. But just like with the other curved mirror, those angles are measured to the normal line, and the normal line curves as the shape of the mirror curves. So let's start with a light ray above the principal axis. Here comes our light ray. When it hits the mirror, it's going to reflect. When a light ray hits a mirror, it always bounces. And when it bounces, it's going to have a reflected angle equal to its incident angle, but that's going to end up bouncing it away from the principal axis. Now, what if we have a light ray that is farther from the principal axis? So a light ray up like this. As this light ray comes in and hits the mirror, every time a light ray hits a mirror, it's going to bounce off. It reflects with a reflected angle equal to the incident angle. Now, this line was coming in parallel to the one before, but the angle it makes with the normal line to the mirror has changed because the mirror has curved farther. So this light ray not only is going to bend away from the principal axis, it's going to bend even more away from the principal axis. Let's draw some light rays below the principal axis. So here's a light ray coming in below the principal axis. When it hits the mirror, it's going to bounce, it's going to reflect so that its reflected angle is equal to its incident angle. All of these things are exactly the same as they were for the mirror that was curved the other way. But again, because of the curvature of the mirror, this light ray is going to bend away from the principal axis instead of toward it. Now, when we did this last time, we found that all of the light rays that we drew converged on a single point, and that point was the focal point of the mirror. These light rays don't converge. These light rays are spreading out as they go away from the face of the mirror. But we saw this with the second image we drew with the converging mirror. And what we had to do then is the same thing we're going to have to do now. We're going to have to draw these dotted lines, these virtual light rays behind the mirror. The dotted lines that show us where the light ray appears to have come from. So there, and there, and there. And yes, I cheated. I had already picked a focal point back here for my mirror, and that's why my lines line up as nicely as they do. If you're trying to draw along, which is a good idea, your light rays aren't going to be quite as pretty unless you happen to sort of skip ahead and know what the answer was. So this point here, which we'll label with a capital F, is the focal point for this mirror. And the distance between it and the mirror itself will be the focal length of the mirror. Now, it turns out, and this will matter on Wednesday when we put the numbers in, this focal length is not exactly the same. Because it's a diverging mirror, we're going to give that focal point, that focal length, a negative sign. It's also on the back of the mirror. It's on the negative side. We'll talk more about that on Wednesday. Don't worry too much about that today. For right now, what I want us to see is that with a diverging mirror, parallel light rays spread out after they bounce off of the mirror, but they spread out as though they came from a single point. And that single point is the focal point of the mirror. So a light ray that comes in parallel is going to bounce as though it came from the focal point. And a light ray that's trying to get to the focal point on the back of the mirror won't reach it because the mirror is in the way. But when it bounces, it'll go out parallel. Ray diagrams for diverging mirrors are a little bit harder because of this, but we can do it. I have full confidence in you. So let's get rid of our sort of sample lines here. And let's figure out what happens when we have an object whose image we're trying to find. All right. So I'm going to make myself an object, I don't know, here. Here's my arrow on top. If I were going to do the math with this, I would measure the object distance and the object height, but I'm not going to do either of those today. I am going to draw my light rays. I'm going to draw exactly the same 3 light rays that I drew for the converging mirror. These are also the same 3 light rays we're going to draw when we draw ray diagrams for lenses next week. So, ray number 1 is the principal ray. The principal ray comes in parallel to the principal axis and goes out through the focal point, or as though it were coming from the focal point. The ray that comes in always has to go through the top of the arrow. So here comes our light ray. It goes until it hits the mirror. When it hits the mirror, it bounces. Light rays always bounce when they hit a mirror. It's going to bounce as though it's coming from the focal point. So away goes my light ray. My principal ray comes in parallel to the principal axis. It bounces and goes out as though it's coming from the focal point. My next ray is my blue ray. Not blue ray, but blue ray. The focal ray. The focal ray comes in heading for the focal point. With the diverging mirror, it won't get there. It'll hit the mirror first, but that's okay, because then it's going to bounce and go out parallel to the principal axis. So here comes my focal ray heading for the focal point, but it hits the mirror. When a light ray hits the mirror, it bounces always. And because this light ray was heading toward the focal point, when it bounces, it goes out parallel to the principal axis. And there it goes. Now, it's worth reiterating. I've said this before, but I'll say it every time. Every time a light ray bounces off of a mirror, it follows the law of reflection. The reflected angle is equal to the incident angle, but those angles are measured to the normal line, the perpendicular line to the curve of the mirror. All right, the last light ray that we'll draw will be the central ray. The central ray comes in to the center point, the point where the principal axis meets the mirror. And it's going to bounce off with the same angle below as it has above. But just as we did with the other two, we're not going to use the central ray to really find the image. We're going to use the central ray to check our work on our image. So the image should be where the bounce, like the reflected principal ray and the reflected focal ray meet. They don't cross on this side of the mirror, which tells us what kind of image are we going to have? We're going to have a virtual image, an image behind the mirror. So I need to draw those dotted lines, those virtual light rays behind the mirror. I'm drawing backwards from the reflected ray, backwards from here, for the principal ray, and then backwards from here for the focal ray. And now we can check our work with the central ray. So the central ray should bounce off of this central point. When it goes backwards, it should intersect the same point where the other two rays crossed. And do those two angles appear to be basically the same? They do. So we feel good about the point we've chosen for our image. Now, to draw the image, we just draw an arrow. The light rays that we draw technically just find the top of the image, so we just draw a line from where they cross to the principal axis. And now we can do our lost. What is the location of this image? The location of this image is behind the mirror. The orientation of this image is upright, or right side up. I don't care which one you want to call it. The size of this image is smaller. And the type of this image is what? Yep, it's a virtual image. It's a virtual image because it's behind the mirror. It's a virtual image because we use dotted light rays to indicate where to form the image. There are no light rays back here. We couldn't put a piece of paper behind the mirror and see an actual image the way we did with the, or the way we will do. Yeah, the way we will do with the mirror outside in just a few minutes. All right. It turns out, and I'll let you play with the optics bench to see this a little bit, it doesn't really matter where the object is for a diverging mirror. You're going to get the same image characteristics all the time. The images are going to be upright, and the images are all going to be virtual. The advantage of a diverging mirror has to do with its shape. Because of the shape of the mirror like this, it can actually gather light from a bigger area, maybe, in front of it. With the converging mirror, it can only gather light from objects where the light rays can actually hit the mirror and be reflected off of it. So this mirror can be used in situations where you want to be able to see a large area. If you think about the mirrors in convenience stores that you think about up in the corners of the convenience stores, those mirrors are diverging mirrors so that somebody can see the whole store from where they're standing. Now, there is one downside of this. Whenever you create an image with a diverging mirror, the size is going to be a little bit smaller. This isn't a big problem, except for one thing. Our brains use size as an indication of distance. So when your brain tries to figure out how far away something is, you've got binocular vision, right? You've got two eyes, you have depth perception. So your brain can use the different images from your two eyes to figure out how far away something is. You can play with this by holding your finger up and opening and closing your eyes and seeing how your finger moves from place to place. But when we're looking at a picture, something like that, we can't use depth perception. And so what our brains do is they know that things that are farther away appear smaller. So that means that an object in this mirror is actually closer than it appears. An object in a diverging mirror is closer than it appears. Because the diverging mirror's image is smaller, then your brain is going to think it's farther away than it is. Where have you seen those words before? They're not so much on car rearview mirrors as they used to be, but there's a famous scene in the movie Jurassic Park where it has that little image at the bottom. No? All right. Well, I tell you what, for today's secret question, tell me a movie that you really love and think I should watch. All right. I think that's good for diverging mirrors. I'm not going to go through this with the optics bench. You guys can follow along with that. But I think you should be set now in terms of mirrors to do the optics bench, to do your concept builder, and don't forget about your UT Quest. You can't start the quantitative mirror problems yet, not until after we've done the lecture on Wednesday about solving these problems with the lens mirror equation. But if you didn't do all of the ones from last week or before the break, you got that big assignment that's due next week. All right, y'all have a great day. What I want to do right now is I want to prove to you that a real image can actually be created on a piece of paper. So we have my front door to my house. There we go. It's nice and red. And if we look at the same curved mirror we saw earlier, we can see the red image of the door. Now, this object is way beyond the focal length of this mirror, which means I should be able to create the image on a piece of paper. So if the camera goes behind, can we see that? We can. Look at that. An actual real image on the piece of paper. I'll tell you, the first time I saw this, I realized that I had not believed in real images until I actually did this. Cool, huh?